Hello, I'm going to present our paper LIC-Fusion 2.0 LiDAR-Inertial-Camera Odometry with sliding window plan feature tracking. I'm Xinxin Zuo. This is a joint work with Yulin Yang, Patrick Geneva, Jiajun Liu, Yong Liu, Guoquan Huang, and Mark Polyphis. As we all know, LiDAR's cameras MUs have different characteristics. The motivation behind this work is trying to use the best of each sensor modality for robust and accurate post-estimations. Besides, starting from our previous work LIC-Fusion, the data association for sparse LiDAR feature is always error-prone. Actually, tracking sparse LiDAR feature is almost unattempted in the research community. Most existing methods just track sparse LiDAR features in a way like SAP. However, considering an EKF framework, without iteratively updating the data association, how to make data association reliable and accurate once forever. In addition, consistency is really important for an estimator, since we not only need high accuracy state estimations, but also the errors of the estimations should be well quantified. Then how to design a consistent estimator viewing measurements from LiDAR, MU, and camera. The contributions can be summarized as follows. First, we propose a LiDAR sliding window plan feature tracking method with probabilistic outlier rejection. Secondly, we develop a consistent and efficient LiDAR-Inertial-Camera odometry. In addition, we perform in-depth observability analysis to identify degenerate cases with respect to the LiDAR-MU calibration parameters. Finally, extensive evaluations of consistency and accuracy in both Monte Carlo simulations and real-world experiments are conducted. The framework of the proposed system includes two main stages, the propagation and the update, which follows a filter-based MSCKF pipeline. The estimated states in this work including MU states, the extrinsics between camera and MU, the extrinsics between LiDAR and MU, the cloned camera poses, the cloned LiDAR poses in a sliding window. The point features denoted in global frame G, and the plane features denoted in anchor frame A. Since the propagation and the updates from camera measurements are trivial and kept the same as MSCKF. Here, we will talk about the update with sparse LiDAR features. With the closest point representation of a 3D plane feature, we denote the normal vector of this plane by n and the distance from the origin to the plane by d. We can compute the distance between a point and a plane by this equation z. We'll keep only salient planes in the state vector and marginalize most plane features for efficiency. After linearizing the distance residual at current best estimates, we can marginalize the plane features by the left non-space matrix n. This non-space operation is valid without pre-vectoring because of the special form of the Jacobian Hn with respect to the noise Nf. After illustrating the update step, it comes to a question of how to associate raw LiDAR points to plane feature. Here we have a simple example of tracking planar features from the ground frame to the radar frame. Inspired by LOM, we firstly extract planar LiDAR points with low curvature. A point I in the green frame is associated to its closest triangle GKL in the red frame. We also make sure that no LiDAR point measurement is reused to prevent reusing information. For instance, the point H won't be associated to point K since the triangle GKL has been associated with point I in the green frame. All of these tracked planar points are assumed to be sampled from the same 3D plane. Thus, we can have multiple observations of the same plane across multiple frames. Is this data association good enough? The answer is no. For instance, a point I on the floor might be associated to its closest triangle GKL on the wall. However, it's definitely incorrect. Then how to reject these outliers? Here we resort to the norm vectors. The associated triangles should have similar norm vectors because they are assumed to be sampled from the same plane. We get the differences between two norm vectors by this function z. Z will be 0 if the two triangles with norm vector n1 and n2 are parallel. We'll take Manhattan-based distance test over Z to reject outliers. This test will take account the uncertainties from both the raw LiDAR points and the relative pulse between LiDAR frames. After tracking a point from frame L0 across subsequent frames L1, L2, L3, we can get multiple observations for the same 3D plane. Thus, we can initialize a 3D plane accurately with these observations and reject the outlier data associations effectively. As the observability of the visual-inertial subsystem is well studied, we conduct observability analysis for the LiDAR and IMU subsystem. By checking the non-space of the observability matrix, we can find that the extrinsics between LiDAR and IMU are observable under general motion. However, there are several degenerate cases, such as pure translation and the one-axis rotation only. Just keep in mind that under one-axis rotation motion, the translation between LiDAR and IMU will become unobservable along the rotation axis. We will conduct an experiment to verify our theoretical findings. In the simulation, we conduct Monte Carlo experiments over 12 runs in a synthetic room with plane structures. We examine the performance of the system starting from ground truth extrinsics or from perturbed backed extrinsics and study the effects of online calibration. The results shown in this table suggests that starting from bad extrinsics, well with online calibration, is able to get comparable results with starting from ground truth extrinsics and disable the online calibration. The bounded NEES error demonstrates the consistency of the whole estimator. We further check the convergence of the LiDAR-IMU extrinsics. As shown in this figure, the 6-off rigid transformation and the time offset between LiDAR and IMU are observable under general motion. We also test a typical degenerate case, where the sensors move around the y-axis only. Then the third dimension of the translation between LiDAR and IMU cannot converge. This result confirms our theoretical analysis described before. We also perform extensive real-world experiments. In this teach building scenario, there are challenges from sudden illumination changes, motion blur in images, degraded structures like long corridors for LiDAR, and highly aggressive motion. 6 methods are compared, including the proposed LIC-Fusion 2, the visual-inertial subsystem OpenVINS, the LiDAR-Inertial subsystem, and the LiDAR Odometry LOM with IMU measurements in a tightly coupled way termed the LIO map, and our previous work, LIC-Fusion. The proposed LIC-Fusion 2 is robust and outperforms the others on most of the sequences regarding final drift error. We also test the method with ground truth trajectory from motion capture in a Vicon room. As you can see, these scenarios are very cluttered, which poses significant challenges for LiDAR feature data association. The proposed LIC-Fusion 2 outperforms the others in a large margin. Here I'll show you a demo on real-world experiments. In this sequence, inside a teach building, we go straight along the corridor. Go upstairs, turn around, and go downstairs. Go along a long corridor. And stopped at the same position where we started. We can see the final drift error is less than 1 meter in a whole trajectory of 237 meters. This is the test under highly aggressive motion. We shake the sensors as strongly as we can. The proposed LIC-Fusion 2 is robust and works pretty well. This shows the test in the Vicon room scenario. To summarize, we propose a LiDAR-Inertial-Camera Odometry with a sliding window LiDAR plane feature tracking method, which enables constraints across multiple LiDAR frames. A new outlier rejection criterion taking into account the uncertainties from both the raw LiDAR points and the relative pulse between LiDAR frames is advocated. The proposed estimator is efficient, and most importantly, it's consistent with the fusion of LiDAR, IMU, and camera. We also perform in-depth observability analysis of the LiDAR-Inertial subsystem. Finally, the proposed method is extensively tested on both simulation and real-world experiments. The results demonstrate the proposed method is robust, consistent, and with high accuracy. Thanks for your attention.